So first of all, welcome. Thank you for coming. Happy birthday, Tyler, wherever he is. Tyler, where are you? Yes! That's my astronaut right there. All right, so a lot of you know I'm unhealthily obsessed with anything space. So I figured I've got you here and you're captured, and so you have to listen to me talk about this. So here's what I'm going to do for the next little while. But first, there's one logistics announcement. I think there's a lot of people's bags in the area here, so it's going to happen around 10. We have this whole section to us, but they open the rest up to the public, so we should just, any stuff that you want on your own, put it in this like back section back here. So if that's your bags back there, then do that. All right, so now I'm going to dive into something that I'm super nerdy about, and I was thinking about talking about on my last birthday, but I never got around to it. So now that I have you, I'm going to force you into it. And that's cosmology and astrophysics, and basically a short introduction to everything that ever has been or will be. So very small topic, right? So I'm going to do this in 3 steps. One is to try to explain a little bit of the scale of the universe, because it's a very hard thing for humans to get. And then talk about where everything came from and then where everything's going. So to start off, the universe is just bigger than anything we can possibly imagine. Humans are very good at thinking arithmetically or linearly. We're not good at thinking geometrically and exponentially. So it's almost impossible for us to really appreciate how big things are. But I'm going to try to do it with some models here. So when you think about the solar system, you often see pictures like this, right, of like sun and planets. But often they're a lot bigger and a lot closer than they actually are in real life. So what I want to do is do like a little experiment here and say, if this beach ball, which we were waiting half an hour to make this happen, so I'm very happy we have this beach ball. But let's say this beach ball were the size of the sun. Relatively, how big do you think the Earth would be?
Basketball.
All right, I have basketball. I have little here. Testicles too big. What it would be? So I ordered some marbles from Amazon. It's the one thing I didn't get here, but it would be ½ inch in diameter. It would be a teeny tiny little thing down here. It would be that small. Yeah. And so this is actually a scaled picture of the solar system. You can't even see it. So Jupiter is the big one here. And actually, the projector's a little off, but the Earth is so small, it's over here, and you can barely even see it compared to the sun. And you can see here, this is just like a subsection of the sun with the Earth placed in, relatively speaking. That our sense of size is just so much smaller than anything that actually exists on an interplanetary or solar scale. And the sun itself is actually pretty small in the grand scheme of things. So as we all know, the sun is just a star, right? When you look up in the sky, those are all objects that have all the same properties as our sun. But if you look at this, you can see sun is very little. There are some really gigantic stars. In fact, so big, this is one scale going all the way up to Arcturus, that's that giant one. And then, I wish this were a little better adjusted, but Arcturus is now this really small one. So it goes from that to this, and that goes all the way up to these giant stars. Antares. And Antares is even smaller than this next one, Canis Majoris, which for a long time was the largest star ever known. And so if you zoom in on this thing, that's the sun in the scale of Canis Majoris. So to give you some little idea, so if this were the sun, again, we could fit about 1.3 million Earths into the sun. But if you look at Canis Majoris, you could fit over 1 billion suns into Canis Majoris. So that's the kind of size that we're talking about. Yeah. And just to throw in here, feel free to throw questions out. I'll do like a little thing at the end, also for questions, but if things come up, feel free to just jump in and yell. We talked a little about size of objects and planets and solar systems, but what about distances between things? And really that's, I think, the thing that's even more vast and more incomprehensible to us. So, let's think again. If this beach ball were the sun, where do you think the Earth would be? How far away?
Outside.
Yeah.
One maritime plaza.
Few blocks away. Melanie.
Japan.
All right.
At the bar?
Not quite that far. The answer is about 375 feet. So about, yeah. Yeah, I know. I oversold it, right? I oversold it. Yeah, we're getting there. So about a football field away. So it would be a little marble a football field away. And now let's. Sorry. Oh yeah. Hello. All right. Now let's up the ante a little bit. So if this beach ball were the sun, where do you think Pluto would be? Pluto being the farthest, well, not really a planet anymore.
Jersey Shore.
The mission.
LA.
The mission.
Kansas.
So it would be a little bit past Alcatraz. That's how far away it would be.
That celestial dwarf is definitely a planet.
Yeah. And so if you look at the actual orbits of the planets, it's not the kind of like everything big and close to each other. But even here on this map, the sun is a little tiny dot, and especially to get to the outer planets, the distances are just vast, and then just endless emptiness in between them. And what really then even dwarfs that is when you think about between stars. So we have our own solar system, all the planets we know. But then you look up in the night sky, you see thousands of stars, and there are billions and billions of stars beyond that. But the closest star to us is called Proxima Centauri. And I'd like to have you guys guess a little bit, again, if the sun were this beach ball, where do you think the next nearest star, Proxima Centauri, would be?
Jersey Shore.
Jersey Shore? I heard that.
Mars.
Texas?
San Bernardino.
All right. All right. For once I got you, you're actually all underestimating. It would be about 19,000 miles away, which is half, like all the way to the opposite side of the Earth, and then around again half again.
Is that on the Jersey Shore? Yeah, he was actually
Yes.
going the other way.
Exactly. So interstellar distances are just dwarf anything else we can think about, and again, that's all empty space in between. And then when you start to zoom out in the galaxy, and our galaxy is called the Milky Way, which is made up of about 100 billion stars. We can see here we've got our location in the Milky Way, which is we're on one of the outer bands of this spiral galaxy. And that circle they have there is, they made it 300 light years. And light travels at 186,000 miles per second. So 1 light year is about 6 trillion miles. So that's the kind of distance we're talking about here.
What's the middle of the Milky Way?
Sorry, middle of the Milky Way, we can get into that. Things get denser and denser, more and more stars, and at the core there's a supermassive black hole, as there are in most galaxies. But again, to give some sense of size of how big the Milky Way is, let's say again, this beach ball were the sun, how big do you think the Milky Way would be? It's a disk, a flat disk. How wide do you think that would be? Any guesses?
The size of our solar system.
To Neptune.
All right, I think you've caught on. So it's about, it would be, compared to this beach ball, about 500 million miles, which is about the orbit of Jupiter. So if you're trying to think about scale, things get pretty insane pretty quick. So in reality, the actual width of the Milky Way is about 100,000 light years. Which means, again, light is the fastest thing in the universe. Nothing can go faster than that. And again, you can only, we see with light, right? So if something happens on the other side of the galaxy, it would take 100,000 years for us to see it. We'd be looking into the past as we observe that. And to give another sense of how big this is, let's think about how long it would take to get to some of these places. So the fastest spacecraft ever built by man is Voyager 1, which is a probe that was launched in the 70s and is now just left the solar system a few years ago, traveling 38,000 miles an hour. So if you were to try to travel at the fastest that humans can do, it would take you 11 years to get to Pluto, 73,000 years to get to the closest star, and almost 2 billion years to get across the Milky Way. So when we talk about these distances, it's a little sobering.
What about the Millennium Falcon?
Yes. We'll hope for them.
Light speed 80.
And so to zoom out, we were just talking about the galactic scale, but then of course we're only one of about 100 billion galaxies. So here is a map of what's called our local group. So we have the Milky Way, which is a fairly large galaxy surrounded by some of these dwarf and globular galaxies. The Andromeda Galaxy is the closest major one, which is about 2.3 million light years away. So we're 100,000 light years across, that's 2.3. And then if you zoom out further, you can see every single point of light you see here is a galaxy. And you see our local group is right there. And then we become part of this. Our bigger group is called Virgo Supercluster, which is this green area here. And then if you zoom out way out, there's a massive agglomeration of superclusters called Laniakea. And then if you go even further out, this is what the universe looks like at the furthest zoom out we can do. And every point of light you're seeing here, which all bleed together, you can see, but every point of light, minuscule here, is a galaxy. Because we can see them all. At least this is the observable universe. So when we look out in telescopes, we can see about 13 billion years into the past, which is going to 13 billion light years away. And this is the picture that we've come up with of every galaxy out there. And you can see it creates this kind of spider web where galaxies attract each other and create these webs. But this is just scales that are truly unimaginable to humans. So, as well as, I wish we could, all right, text working great. But anyway, so that was kind of the galactic scale of emptiness, but we can also go to the subatomic scale and the very small scale of emptiness. So, as you guys all know from like old chemistry class, everything's built on atoms, right? That's the kind of fundamental building block of how everything works. You have protons in the middle, protons and neutrons forming the nucleus, and then electrons orbit around it. And those are the elements you see in the periodic chart, and that makes up all molecules that we're made of. Another way of looking at it with different orbits. But here's a question for you too. So nuclei held about 99.9% of the mass of every atom. But let's say this was the nucleus of an atom. How big do you think the atom would be?
Bigger in this room.
Bigger than this room? This is the nucleus. The beach ball's the nucleus. How big's the atom?
Sacramento.
San Francisco. I did that.
Sacramento.
Sacramento. All right. So if you actually did the calculations about, if that were the nucleus, the diameter of the atom would be about 66 miles, which means it would stretch from here to Stanford. So that's how, and the electron to that would be invisible in terms of how small it is. So pretty much everything you see, all of you and me, we're all empty space between protons and electrons when you actually think about it. Yeah, so again, in sum, the vast majority of the universe is emptiness, both on the massive scale and the very small scale. And wait, Zach, can I ask you, I want to make sure I don't go super over time. I've got a little clock. Oh wait, actually.
9:42.
Yes, all right, cool. All right, so I'm going on to step 2, which is the origin of everything. Like, where did we all come from? How did this all start? So, as you probably heard, Big Bang, right? This is where everything starts. 13.8 billion years ago, everything that has ever existed and will ever exist existed in a single point and exploded. And this is what physics called a singularity. It was infinitely small, infinitely dense, infinitely hot, and it curved space around it infinitely. So space itself, not just everything in it, exploded. Nothing existed. There was no empty space outside of it. It's kind of hard to actually contemplate. So what happened after the Big Bang started was just, yes, hold on, yeah. So everything that's ever existed was in one infinitesimal point, and it exploded at the most rapid rate anything's ever exploded. So you have, for instance, in 1 billion trillion trillionth of a second, the universe expanded by 1 trillion 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 times. So to give you an idea of that, that would be as if a penny in this amount of time, in a trillion trillionth of a second, billion trillionth of a second, if a penny expanded into 43 million times bigger than the Milky Way galaxy. And everything basically was hotter than the sun, hotter than anything that we could imagine. It was basically a giant inferno and everything that we know is pure energy. So what is energy when you really think about it? You can think about it in many forms now. Heat, chemical energy, electrical energy, energy of motion. If I'm moving, I have energy with me. Anything with mass that is doing anything pretty much has energy. But pure energy, which is how the universe started, what is that? That's light. And light, also known as electromagnetic radiation, is essentially energy that comes in little packets and little particles. And we call them photons. And that was how everything started in the universe. It was just a whole lot of photons all at once. And photons have two properties, that they're both a wave and a particle. So we can both look at them as a discrete particle that has discrete effects on different other particles, but it's also a wave, like a sound wave or a wave in the ocean. And so when you think about what light is, it's, again, when you think about it as a wave, all waves have frequency and wavelength. And it's just like a high-pitched sound, right? And that means it has a higher frequency and you hear it more often. It's exactly the same with light. So the part of light that we can see is this little bit on this whole scale of how wide these bands can be. So from violet to red, that's what we see with our eyes. But everything else on here, radio waves, microwaves, ultraviolet, X-ray, gamma rays, they're all the exact same thing. They're just either they have more frequency or longer wavelengths. And the way it works is higher frequency means you have higher energy. So this is the high energy end of the spectrum. Gamma rays are the most energetic, and all the way down to radio waves are the least energetic. And so that's how the universe started. But then matter comes into the picture. And matter is anything that has mass. That's how we define it. So protons, neutrons, which make up the nucleus of an atom, electrons, which orbit around it, neutrinos, which are some other things we don't have to get into too much. But the real key is that there's a very famous equation you all know. Now you can't even see it. So up here, you should be able to see E equals mc squared. You all know that, right?
We can see it.
Yeah, so E equals mc squared means energy is equal to mass times c, which is the constant speed of light squared. It's a very large number, 186,000 miles per second squared. But what it means is energy and mass are essentially the same thing. There's no difference between, in theory, between a light beam and you. So you have photons are equal to subatomic particles like protons or electrons or anything else, but it's times this constant that's very large. So it takes a whole lot of energy, a whole lot of photons to make mass. So what happened when the universe first started, you had the most energetic light possible, most energetic waves. It was gamma rays primarily. And what E equals mc squared ended up being is you have that energy turned into mass spontaneously because it was so high energy. And what happened is it would split into matter and antimatter pairs. Now, antimatter sounds kind of like sci-fi and crazy, but it's actually not really. All it means is it's the equivalent of mass, everything that we're made of, just everything has the opposite charge. So just like proton has a positive charge, electron has a negative charge, antimatter is just the same, but the charges are flipped. So if we, for instance, were made of antimatter, we look exactly the same, we would just probably call the charges opposite things. But the way that matter and antimatter interact is as soon as they meet each other, they immediately annihilate and become pure energy. They create light or gamma rays or whatever rays that happen. So what happened here is that you had all this energy was released in the Big Bang. You had everything converted immediately to matter and antimatter. What should have happened is that the matter and antimatter cancel out and turn back into energy. But for reasons we still don't understand, there was an imbalance. For about every billion particles of antimatter, there's about 1,000,000,001 particles of matter. And that's due, we think, to quantum fluctuations, things we don't quite understand. But because there was this imbalance and because there was 1 out of 1,000,000,000 parts of matter were more positive and negative, everything we know and see exists. Otherwise, we all would have just become light beams once again. And so what happened then was you had the Big Bang happen, you have the universe inflates massively immediately, again, almost infinite temperatures dropping pretty rapidly, but this imbalance of matter and antimatter means there's some matter left over, And that is at such a high heat quotient that you can't even form protons. It's quarks, which are the subunit of that. But around 1/1,000,000th of a second after the Big Bang happened, things cool down enough and things expand enough that things, because temperature, right, is just the measure of how fast matter is moving somewhere. So when it cools down as it expands, then the quarks start moving slow enough that they bind together and form protons. So from 1/1,000,000th of a second after the Big Bang, every single proton in the universe, every proton in your body, my body, everything else on the Earth was all formed. There's no protons ever formed before or since. That's where everything came from. You had then a few more minutes where you just had protons flying around freely. And about 3 minutes after the Big Bang, you had the beginning of atomic nuclei form. So you had hydrogen, which just has one proton, and helium, which has two protons, start to form. And that's where basically all the hydrogen in the universe comes from 3 minutes after the Big Bang. So all like H2O, every drink of water you have, every hydrogen atom in that was formed 3 minutes after the Big Bang, this exact time and place. Then a little later, you have, when things cool down more, you basically have 300,000 years of electrons bouncing around, and you have these protons, but electrons never bind with them to make atoms. So it's just free electrons bouncing all over the place, and it's just kind of a cosmic suit, like a plasma, which it actually resembles the surface of the sun a lot, if you think about that. And so that was 300,000 years, the entire universe, as it expanded, again, like millions of times bigger than our galaxy, was just essentially a giant sun, if you think about it. And then what happened at 380,000 years ago was the universe became transparent. So this is when electrons bound to protons, and all of a sudden the photons, which are the light particles, were bouncing around, were no longer running into these electrons all the time. So they were actually able to pass through everything undisturbed. And finally things became visible. Because before that it was basically this pale drawn over everything. And now light passes through. So what that means is we can see it. So if we look with our farthest telescopes, looking as far back in the past as we can, because again, light has a definite speed, right? So it takes time for it to get there. So the farthest back in time we can look is also the farthest distance we can look. So if we do that, and we look back to just 380,000 years after the Big Bang, we get what's called the cosmic microwave background radiation. So this is basically a baby picture of the universe. And if you think about it, we're making a three-dimensional thing two-dimensional. So really this would be like a spherical thing. If we're in the middle of a sphere looking around, this would surround us in every direction. And this is all the light that was finally able to pass through once all those atoms formed. And we can see that now, and actually it's one of the biggest pieces of evidence for the Big Bang. And it also shows us evidence for the inflationary theory. It shows us how uniform the universe is. That it's basically all these little things delineate differences in temperature, but these are only about 1 in 1 billionth of a degree difference in temperature. The universe is almost completely uniform. And this is another way of thinking about it is like over time, if we look back to the cosmic microwave radiation here, and we're here in the present, we're looking both into the past and into farthest distance we can to see it. So after this happened, you had darkness for 300 million years. Just atoms floating around for no purpose, until you had stars born. And stars are really the building block of the universe. And that's really what makes everything that's interesting and that makes life possible. So what is a star? Sun is a star. And how do they form? So as you have atoms, basically for 300 million years floating around, gravity slowly acts on all of them, and they start to conglomerate, and they start to create clumps and dust, and eventually they get into these giant, what's called accretion disks. And gravity pulls them closer and closer to the center. Angular momentum also makes them start to spin around. And if you get enough gas, it's hydrogen and helium now, is everything that's created at the beginning of the universe. You get enough of it in one place, it compresses down by the force of gravity, so much so that it ignites into a star. And that's where how all stars are born. And just like our sun, all stars have a core that burns hydrogen through nuclear fusion, just in the middle where it's much harder than the outside, and the energy flows outward. So fusion, you've heard of like a hydrogen bomb, that's exactly what it is. It takes two hydrogen atoms, and it smashes them together. They each have one proton. Smashes them together, it creates one helium atom that has two protons. Now, when that can only happen at the insanely high temperatures that are about 5 million plus degrees in the middle of a star, when there's that much gravity, that much pressure. And what that means is, again, we're going back to E equals mc squared. When that happens, the atom loses a very tiny amount of mass, and that mass is converted into pure energy. And that's where all the photons are released, and that's where all the sunlight and everything else that comes from the sun comes from. So you have here again, core where nuclear fusion is taking place. It pushes energy outwards, just as gravity pulls inwards, and it creates a kind of balance in stars between this outward pressure from fusion and inward pressure from gravity. And you can also see here all the different parts of the sun and different stars. Interesting thing is, so all the light that we see that is bouncing off of all of us right now, or particularly in daylight, is formed in the core of stars where this fusion takes place. They have to go all the way to the outside of the sun. It takes them about 300,000 years to get from the inside to the outside of the sun. Once it hits the core, it travels the speed of light straight to us and gets to us from the sun in about 8 minutes. And nuclear fusion, as I said, it takes smaller atoms and combines them into bigger ones. So you start with the most basic stuff, which is hydrogen, which is just one proton. That creates helium. Then, when you have bigger stars, when they run out of hydrogen, they put helium together, create oxygen. Once that runs out, they put oxygen, helium together, create carbon, so on and so forth down this list until you get to iron. And what happens when stars start trying to fuse iron is it actually takes more energy to fuse at a higher level than it does to do it at a lower level. So that's why we have, I don't know if you know, there are two types of atomic bombs. There's fusion bombs, which do basically what stars do. Then there's the original one, fission bombs, break atoms apart. So everything above iron in terms of how many protons they have, you get more energy by breaking them apart. Everything below iron, you get more energy by putting them together. So what happens when stars do this and they hit, so everything up till iron, all these things are created in stars through their natural fusion things. This is the periodic chart of all the elements we know, everything makes up everything. Only a few of them, right, are on here. We have helium, hydrogen, oxygen, carbon. So where do the rest of them come from? So it comes when stars run out of fuel. So there's a whole lot of types of stars, but it's really all dependent on how big they are and how brightly they burn. And they're all basically the same, it's just everything's dependent. This is a little map that I won't go too much into, but if you're burning hotter, you're more blue, that's a more energetic light. If you're burning lighter, you're more red. The bigger stars are, the faster they burn. For instance, what happens when you start to run out of this fuel, for instance, the sun is a pretty typical star. When it runs out of hydrogen to fuse, it'll start fusing helium. It'll expand into a red giant. Once it runs out of that, it's actually going to collapse back in on itself. Everything on the outside will be expelled, and it'll become what's called a white dwarf, which is a very small, very dense star, which will be about the size of the Earth, but way as much as the sun. And many stars do this, and there are two ways then that stars see the rest of the universe. So these are supernovas, which you've probably heard about. And there are two types. One is type 1a, which is when you have a white dwarf, like what our sun will become, and another star in what's called a binary system. And about half of all stars are in a binary system where they rotate around each other and are very close. So when one turns into a white dwarf and starts sucking matter out of the other one, at a certain point it passes a point where the weight of it is too much to balance out the outward pressure, and it explodes. Secondly, you can have really massive stars, much bigger than our sun, that are so big that when they'll fuse things all the way up till iron. But then the second they do, because again this energy thing changes, the gravity then outweighs the outward energy, and it all collapses in a microsecond. All this weight, and then it all bounces off each other and creates a supernova. And these things are so energetic and so bright that they actually outshine entire galaxies. So brighter than 100 billion stars when this happens. And when it does, all that heat and all that pressure creates every single other element on the periodic chart. Everything that you're made of, all the gold that you're wearing, all the iron in your blood, everything. And that's where everything you know that's beyond just a very basic level comes from, is from supernovas. And they seed the universe. This year, but what happens is they explode, they blow out all these elements into the universe, and they then become stars afterwards, or become planets. So our sun is about a third generation star, so there were many, many stars that came and exploded before us, and that's what created everything that we know now. These are some other nebulae, this is called the Eagle Nebulae. That's actually about 600 trillion miles tall. That's just a gas cloud where stars are born. So 4 billion years ago, our solar system starts to take place. So let's say this is our sun. We have a gas cloud agglomerating around it. Once it ignites, it kind of pushes some of the gases outwards, and then you have the planet starts to take shape from all the dust and stuff that's rotating around it. So you have here a picture of, in the inner part where the sun is so bright that it's hot, all the ice and water is melted, and that's where you have some of the more solid planets form. In the outer part, the gases aren't affected as much, that's where the giant gas planets form. So the Earth was formed right about the same time the sun was born, about a couple 100 million years after, from all this stuff that was floating around it. And for a long while it was just pummeled by asteroids, and it was red hot and basically a lava hellhole. But eventually the solar system subsided, all the planets formed from all this detritus. Gravity just pulled them all together. And the Earth formed with a red hot molten core, which again is left over from these red hot asteroids and everything hitting each other. And we get cooler and cooler to the outside until we get to our surface that we live on. Another interesting thing is, where did the moon come from? The most dominant theory is that there was a planet about the size of Mars that crashed into the Earth about 4 billion years ago, like this, spewed out about half the mass of the Earth, which started rotating around. A lot of it fell back to Earth, but the remainder formed the moon, and that's where it came from. Again, there's a little text missing, but in the story here is that we're pretty lucky in terms of where the Earth is. We're at a good distance from the center of the galaxy, where the stars are much denser, and you'd see many more supernovae that would probably wipe out any life on Earth that would develop. We're in the Goldilocks zone, what's called from our star, where liquid water can take place. It's not too cold, not too hot. We're protected from most of the asteroids that would hit us by Jupiter, which is, its mass tends to fling asteroids out of the solar system. We have a magnetic field, which could get into a little later, that protects us from radiation from the sun, and we have a large moon that keeps our seasons stable, that keeps tides going and everything working. So quick history of the Earth. You have simple life. Earth is about 4.6 billion years old. You have simple life starting 4 billion years ago, and single-cell life all the way up till 500 million years ago. So it's a pretty recent phenomenon in terms of how old the Earth is. And you have dinosaurs and everything else happen just in the last 500 million years. Yeah. And then if you get to us, we're going back about 1.2 million years ago, we'll say, first proto-humans. And beyond that, it takes quite a long time. 10,000 BC-ish is when we invent agriculture, and history starts about 3,000 years ago. So again, in the large scheme of how long it takes for things to happen, a little timeline from Big Bang all the way till now, we're pretty late in the game. So to do another kind of exercise in the scale, if you think about the history of the universe as an entire calendar year, so Big Bang happens midnight January 1st, then the first humans appear December 31st, 11:46 p.m. That's how late in the game we are. And you think about biologically modern humans, so people who we would recognize today as not monkeys, but humans, 11:58 and 5 seconds. First agriculture, 11:59, and recorded history, 11:59 and 54 seconds. So we really have not been around too long. All right, that's the history of the universe. And then a quick look into the future. So the universe is expanding, which you've probably heard. And that's, again, a consequence of the Big Bang. Things started out just space, and the thing is space itself expands. So if you think the best comparison is to a balloon. So if you think of every galaxy as a point on a balloon, if you blow up a balloon, every point moves away from each other at the same rate. So that means the farther away you are, the faster away you move. And so that's basically how the universe works as it expands. And so the question is it going to expand forever? So we know it started out expanding, but gravity should work against it, right? Everything attracts each other. So there are two types of matter attracts each other, but there are two types. There's the normal matter we all know, but there's also something called dark matter, which we can sense by its gravitational pull, but we can't see. So light passes through it, we can't see it or interact with it, but it actually makes up more than the real matter in the universe. The other part is something called dark energy, which we don't really know what it is at all, but we just know it acts against gravity, it fills empty space, and it actually makes the universe expand. So we can now do some pretty good calculations that we know this is what the universe is made of, which is pretty weird and surprising. So normal matter, everything we know, you, me, the planets, the stars, everything is just 4% of the stuff of the universe. And again, E equals mc squared, so we have matter here and energy, but it's all the same. So dark matter is 20%, dark energy is 25%. Can't see it here, but also this is something that's changing. At the beginning of the universe, matter made up about everything, and it's slowly, dark energy has been taking over, because the more empty space there is, the more dark energy there is. And it'll continue that way until matter is basically insignificant compared to dark energy. And so what scientists can pretty much now determine for sure is that the universe is going to expand forever. And it won't have a big crunch, it won't come back in. There'll be a heat death, or what's called a big chill. So things will just keep expanding and keep cooling down until basically everything is gone. So eventually, stars will burn out. They have a finite lifetime. And the last stars will form in about 100 trillion years, so we've got some time. But at that point, those last stars will die and there will be no more light in the universe. The universe will go dark. Eventually, black holes will agglomerate and they'll consume everything else, but because of some of the rules of physics, they'll actually radiate out their mass over the next trillion years until there's just radiation that expands into nothing. So not a great future, I guess. But the thing is, the Earth's going to die long before that anyway. Because our sun, as I mentioned, is going to become a red giant. It'll actually expand to the orbit of the Earth, which is here. It'll burn our planet to a crisp. That'll happen in about 4 billion years. But before that, who knows what happens. The moon is also slowly moving away from us, and at a certain point, Earth's gravity may just break it apart, in which case it may just rain down fire on the Earth. You could have black holes and other things shoot massive amounts of radiation at us at a pretty random pace. So if we got hit, for instance, by a black hole shooting a gamma ray blast, it would pretty much destroy all life on Earth. Or you could have typical asteroid hit, which we all see in the movies. So, all right, so I know I'm boring everyone, but I just want to get to my last point, which is what I kind of care about. So it's like, why does this matter? Why do I care about this? So, hey guys, just 1 second. Last bit, I promise. So just a couple points. I think what I love about this and makes me think about it is, one, this gives us a true sense that we are small. We are very small on the scale of things, the scale of history. And we should appreciate just how vast and how much more out there is and not feel too self-important. But some people don't like that, and it makes it feel too small. But I think there's a lot to be said in the other sense, that we're lucky also, that we, as I mentioned, we live, to begin with, at a point in history where we're not rummaging around for food and berries. Our species grew up on a planet that was just in the right balance of everything to make life work. We also live at the right time in the history of the universe. Because if we lived much earlier, after the Big Bang, yes, it would be too hot, we wouldn't be able to see anything. If we lived much later, for instance, if we lived 100 billion years from now, galaxies would be moving so far away from us, so fast away from us that we couldn't see them. They'd be moving away from us faster than the speed of light. So we would actually have no evidence that any other galaxy exists. So we would actually have no knowledge of all the stuff about the universe that we know. We would think that our galaxy is the whole universe. And then the other thing I really love to think about is that we're all connected. Everything comes from the same place, and everything will end up in the same place. If you think about it, the human body, if you actually want to look at the elements, made up of primarily four things: hydrogen, carbon, oxygen, and nitrogen. And the really amazing thing is those are, 3 out of those 4 are the most, are the most common elements in the galaxy and in stars. So we are, in a lot of ways, literally children of the stars. We're hydrogen, oxygen, carbon, and that's us. And we actually resemble the stars more than we resemble the Earth. If you look at the Earth, only oxygen is in common. It's mostly made of metals that we don't really have in our body as much, silicon, aluminum, iron. And again, as I mentioned, every single thing in us, every atom in your body, every piece of jewelry on you, everything came from the same place. We were all born in the Big Bang and in the forge of the nuclear furnace of stars. And that's also where we'll all end up. Every atom in your body eventually will end up being recycled in the earth. Atoms don't leave, they always stay. There's no destruction of them. And eventually the sun will eat them back up in 4 billion years. And we all are stardust in a very real sense. And last thing is we're all special too. There's a great quote. Einstein once said the most incomprehensible thing about the universe is that it is comprehensible. And it's a pretty amazing thing to think about, that we can actually, we can look at all this and we can understand what's going on. There's, you know, the most advanced physics thinks that if you set up all the laws and you set all the parameters right, that everything that we see is dependent on the fact that some of these constants of the charge of electrons, the mass of protons, has to be just right for us to exist. Other than they're a little bit off, stars would never form, we'd fly apart, nothing would exist. In fact, like, in terms of how things are set up, scientists think that it would be about 10 to the 500th power different permutations you could do with this, and we're just 1 out of 10 to the 500th power. To give you an idea, there are only 10 to the 84 atoms in the entire universe. So that's how many different possibilities there could be, and we're the one where we have the ability to exist. And then there's a Carl Sagan quote I love. The cosmos is also within us. We're made of star stuff. We are a way for the cosmos to know itself. And so I'm a pile of a trillion atoms. Somehow communicating to you, we're all a pile of trillion atoms. Yet there's some phenomenon happening where we can actually understand both what we are and what the universe is. And that's a pretty miraculous thing. So on that note, thank you. So I know I went on too long, but I think there's a couple questions if anybody wants. I also have a whole bunch of random stuff overflowing. Any questions, or should we just start drinking?
We should start drinking.
I think we should start drinking. All right, thanks everybody.